Welcome to The Explainer. Today we're diving into the fundamental rules that govern energy and, well, pretty much all change in the universe. We're talking about the laws of thermodynamics.
So what does a pressure cooker have in common with the universe? I know, it sounds a little out there, right? But the answer is that they both play by the exact same set of incredibly powerful rules. These are the principles of thermodynamics, and they tell us how energy behaves in any given system. Let's get into it.
All right, so before we can really wrap our heads around change, we first have to understand what it means for something to be completely still. From an energy point of view. We need to establish a starting line.
This is what we call thermodynamic equilibrium. Think of it as a state of perfect balance. Imagine you've got a gas in a box, and its temperature, its pressure, and its volume are all just holding steady. It's an equilibrium. This is our baseline, the fundamental state that thermodynamics always starts from and returns to. Okay, so if equilibrium is our starting point and our final destination, how do we actually describe the journey that a system takes to get from one balanced state to another? That journey is called a thermodynamic process, and I mean every single change. Water boiling into steam? That's a process. A chemical reaction happening? Also a process. It's the path of change itself. Now, this is where it gets really interesting. We can actually control the rules of the road for these energy journeys. By forcing just one variable, like temperature or pressure, to stay constant, we get very specific, very predictable results. So, first up is the isothermal process. The temperature does not change, not even a little bit. Now, for that to happen, the system has to do something clever. Any heat that flows into it has to be immediately used to do work on its surroundings, so its internal temperature never actually gets a chance to go up. This gives us this beautifully simple relationship. The equation W equals negative Q just means that the work done by the system, that's W, is exactly equal to the heat it absorbs, which is Q. It's a perfect, direct conversion of heat into action. This next one is everywhere in the real world. It's the isobaric process, constant pressure. Just picture any chemical reaction taking place in a beaker that's open to the air. The pressure on that system is just our atmosphere, and that stays pretty much constant the whole time. And finally, we've got the isochoric process. This is where the volume is held constant. To do this, you need a sealed, totally rigid container, something that can't expand or be compressed. Think about that pressure cooker, or a lab instrument called a bomb calorimeter. The volume is locked in. And here's the crucial bit. Because the volume can't change, the system can't do any work on its surroundings. It can't push anything. So, any heat you add is basically trapped inside, and it directly increases the system's total internal energy. That's what that delta U represents. So let's just quickly recap those three. Isothermal holds temperature steady, turning heat into work. Isobaric holds pressure steady, like in that open beaker. And isochoric holds volume steady, forcing all the added heat to just build up as internal energy. So we've managed temperature, pressure, and volume. But what happens if we try a different kind of rule? What if we just completely isolate a system from the outside world, so no heat can get in or out? This is what we call an adiabatic process. The easiest way to picture it is to think of a perfect thermos, something that's so well insulated that nothing gets in, nothing gets out. The system is all on its own, energetically speaking. And the result is simple but really profound. Since no heat can get in or out, any change in the system's internal energy has to come from work. So if the system does work, let's say a gas expands, it has to use its own internal energy to do it. It literally pays the energy bill itself, and that causes it to cool down. Okay, so now that we've got the practical rules down, let's explore something a little more theoretical. The absolutely perfect, most efficient journey a system could possibly take between two states. This is called a reversible process. Now, to be clear, this is a theoretical ideal. It's not something we can actually build in the real world. But it's so important because it serves as the ultimate benchmark, the gold standard that we measure all real-world processes against. So why is this just a theory? Because it has to move infinitely slowly, in a countless number of tiny, tiny steps. This means the system is always in perfect equilibrium. It's so delicately balanced that you could reverse its direction with just the slightest nudge. So why do we care about a process that can't really happen? Because it represents the absolute limit of efficiency. A perfectly reversible process gets the maximum possible amount of work out of a system. It sets the gold standard that every real-world engine is trying to get a little bit closer to.
Okay, so why should you care about all these abstract ideas like isochoric or reversible? How does any of this actually connect back to our world?
Because these are not just abstract ideas, they are the fundamental rules of the game. They're the building blocks engineers use to design car engines and power plants. They tell us the absolute maximum efficiency we can ever dream of achieving, and they explain how every single energy transformation in our world actually works.
And that leaves us with a pretty fascinating thought. This ideal of a perfectly reversible process is the ultimate goal for efficiency. So if we could ever get close to actually achieving it, what kind of technology, what kind of impossible machines could we finally create? It's a question that drives innovation to this day.